Greetings to all of you out there, and thank you for joining us for today's webinar entitled Loop-Mediated Isothermal Amplification, Primer Design and Assay Optimization. My name is Karen Clayman, a product manager here at Lucigen, and I'll be moderating the event today. Go ahead and introduce today's speaker. Tony Rockweiler, a diagnostic research scientist here at Lucigen. Tony previously worked at PPD and Opgen and has over 10 years experience developing molecular biology reagents and diagnostic assays. Tony?
Thank you, Karen. Welcome everyone to today's webinar. We will be discussing LAMP and how it works, examining primers, their design, and how to use Eiken's primer design software. And we will also finally review some LAMP assay optimization. Loop-Mediated Isothermal Amplification was published and invented by Eiken Chemical Company in 2000. As the name suggests, it runs on a single amplification on a single temperature. It uses a polymerase with high strand displacement activity, which allows it to be isothermal. You don't require the 95 denaturation in PCR. Amplification is rapid, so it's factorial as opposed to exponential in PCR. And it can be used for RNA templates with the addition of a reverse transcriptase or by using an enzyme that has both RT activity and DNA polymerase activity. Many of you are probably familiar with PCR. Using that as a baseline, comparing LAMP versus PCR. Again, LAMP is isothermal versus the temperature cycling required for PCR. A big difference is that LAMP requires 6 primers versus the 2. LAMP is very rapid. You can see positive reactions under 30 minutes. The yield is much higher with 10 to 20 milligrams, which makes it amenable to visual detection based on turbidity. LAMP tends to be more tolerant of sample matrix inhibitors. However, it can be very difficult to multiplex due to the additional primers. LAMP has some advantages. It is rapid. It's sensitive and specific with the additional primers. It has the isothermal capabilities, which requires less instrument constraints. Its disadvantages is it's more difficult to design the primers. Most detection methods are not sequence specific. You cannot use hydrolysis probes, for example. It's difficult to multiplex, as I previously mentioned, and they're not suitable for downstream applications, cloning or sequencing. It makes it ideal for certain applications, so detection, point of care, or field-based detection. You can take this and use this for limited resource settings. However, it has a small test menu and is, again, very rapid. It's inappropriate for a large test menu and anything that is unsequenced. You need a properly sequenced target. It is quite useful in diagnostics and particularly in that point of care, point of need, or point of collection situations in molecular diagnostics with infectious diseases, human or veterinary, food testing, environmental testing, and some research applications. The LAMP workflow is very easy with very low complexity with instrumentation because of the isothermal nature. Either a sample can be directly added or a simple nucleic acid extraction heat lysis can be used and placed directly into the amplification reaction with a wide variety of detection methods. You can use real-time or endpoint fluorescence, magnesium precipitation with turbidity, colorimetric, or use an agarose gel. One of the more useful modes of detection is fluorescent detection because it is going to be more sensitive. You'll have a faster time to result with a fluorescent detection. In particular, real-time. Real-time is very useful when we get to the optimization stage. It allows for seeing when the difference between the background and your low positives and allowing you to optimize conditions to create a larger resolution between a positive and negative. LAMP primers. LAMP requires a minimum of 4 primers, and 6 with the inclusion of loop primers. I strongly suggest loop primers. Loop primers allow for faster reactions. There are the F3 and B3, which are your outer primers, and then your FIP and BIP, which are your inner primers, and then again your loops. The FIP also includes complementary sequence that creates an 8th portion of the genome that will hit over here, and that is required to create the stem loop structure, which we'll get to in a moment. One thing to note here is that there's a space between the F2 and the F1C to allow that loop primer to be designed between those two. That will become important later in a few slides. To create the stem loop structure, amplification begins by strand invasion by one of the inner primers, and the strand displacing DNA polymerase extends the primer and separates the target DNA complex in step 1. In step 2, the first product is then displaced by one of the outer primers, and what you end up with is the sequence with the forward complement and the forward, which will allow that stem loop to be created. And this occurs again on the backward sequence, in which your final product here is this stem loop structure. This is the first base intermediate to allow for that factorial amplification. So what you end up with is multimeric DNAs with inverted repeats during this amplification. And so here is your stem loop. From that stem loop, multiple points of amplification can be initiated, whether that's on the F1C or the B2 regions. And what you end up with is a variety of different products that can concatenize and allow for that factorial amplification.
Okay, that brings us to our first poll question. Which description best defines your experience with PCR or LAMP assays? And please select all that apply. Are you scientists working in the lab using PCR? Are you working in the lab developing LAMP assays? Maybe you're not performing PCR or LAMP at the current moment. If you're somebody else interested in LAMP and not working in the lab, go ahead and please type that in the chat box. All right, a number of people are using PCR, Tony, and a few are also developing the LAMP assays at this time. So I'm going to go ahead and stop the poll. Thank you, everybody, for participating.
Great. Thank you, Karen. So to start off with primer design, we're going to a brief overview of the different primers. And what you'll see is that many of the primers have the same length. There are 15 to 25, roughly, mers that is very similar to a PCR primer. The addition of the F1C and the F2 would create your FIP, and then you end up with a total length between 40 and 50 mer for your FIP or your BIP. And then the distances between your primers is important, specifically between the F2 and the F1C, because that's where your loop primer needs to sit. And with what we'll find in a few slides with the Eiken software, acknowledging that distance will become important during your primer design. Excuse me. Basic primer design guidelines. There's many characteristics that can go into this. First, your primers are specified 5' to 3', similar to PCR. Just remember when you're ordering that you are ordering in your correct orientation, because there will be sense and antisense. It's ideal to design against a 40 to 60% GC content. You're going to need an amplicon footprint of 280 base pairs or more to allow room for all of the primers. You should avoid 3 or more on-base or dinucleotide repeats. Both will cause mispriming. Runs of 3 will also cause issues with synthesis and HPLC purification. Primer pairs should have similar TMs with a maximum difference of 5 degrees. One thing, what I mean by primer pairs, it's between your F3 and B3, F2, B2, etc., should be within that 5 degrees Celsius. You should also avoid regions of secondary structure, namely intraprimer homology or interprimer homology. These circumstances can lead to self-dimers, hairpins, or primer dimers instead of annealing to your DNA sequence. In general, you should select the largest delta G value for dimer analysis, a minimum of a -3.5 for optimal design, and then select a smaller delta G for the ends of your primers, a maximum of -4. So, delta G, just as a reminder, is the energy needed to fully break that secondary structure. So having that lower delta G would be more energy to break that strand. So with a dimer, you want the highest delta G possible. So as little amount of energy needed to break that dimer. For hairpins, the melting temperature should be lower than the annealing temperature for the reaction. On average, it should range between 55 and 65 degrees Celsius. The TM for the strongest hairpin should be at least, very least, 50 degrees Celsius and below the annealing temperature. If the TM of your primer is very low, you can try and find a sequence with more GC content or try and extend that primer length a little bit. A few additional tips. So poly-T linkers have been reported to help with speed because it'll help improve the loop formation. I've not been able to empirically prove this myself. I'm not sure on the value, but if you are looking to find more speed, you can go ahead and try and design in a poly-T linker and see if it helps. Mutations, depending on what you're trying to do, whether or not you're trying to detect wild type and mutant, if you're trying to avoid missing any of your strains, which we'll get into in a little bit, it's best to design your primers with mutations located at the 5' ends of the F3, B3, F2, and B2, or the 3' ends of the F1C and B1C, or bury that mutation in an internal region of the primer. Also, to help deal with mutations, use of degenerate nucleotides can be valuable. So the first step to getting ready to design your primers is to choose your target sequence. The proper selection is very important to make sure that you're going to detect of the things of interest and not end up with false positives or false negatives. Strain to strain variation is very important, particularly with bacteria and viruses that have a high variation. So you want to pick a footprint that is conserved across all of the strains that are of interest to avoid those false negatives. And in turn, you want to avoid having any false positives by inadvertently detecting closely related organisms that may be found in your sample. One way to make sure that you detect what you're looking for is to select a conserved region. And this is an example of conserved region without any mutations. These are 7 different strains of Ebola, and this is a very short region that is completely conserved. So this would be a region that you would be able to design a primer and have confidence that you can detect all 7 strains. Conversely, if you try to use this section of a genome, and this is 11 different strains of Drosophila, there's enough variation within this set of sequence that designing a primer in this area would be difficult and still get the coverage you need for all 11 strains. However, if you do have some variation, you can deal with it either by creating degenerate nucleotides or creating multiple primer sets. So with degenerate nucleotides, you can see that if you, in the example here, where there's an R for the UPAC code, you can see that if you put an R here, you'd have a mixture of G's and A's in that location, and you'd be able to detect all 7 strains of Ebola. And that's the same with these other locations, and this Y is another version which contains a C and a T. Another approach is to design 2 different sets here, because there's 2 populations. So you could design 2 primer sets to get your complete coverage and have 2 different assays. You also want to avoid closely related organisms. So once you have a primer set designed based on your strain coverage, you want to blast that design against a database to determine whether or not there are any hits and make sure that you can successfully do that and not have any cross-reactivity. But don't rely on BLAST alone. You are limited with BLAST based on the size of your database and the coverage in the database, so it's strongly suggested to logically pick a set of organisms to test specificity against that might end up in your sample.
All right, the next poll question. What software do you use for designing PCR primers and or LAMP primers? Again, please select all that apply. BLAST, Primer 3, and a couple of LAMP options there. And again, if you have something, maybe one of the vendors for the oligos, you utilize those, that type of software, go ahead and put that in the chat box. Okay, most people are using BLAST for the PCR and PrimerExplorer. Great, thank you.
All right, thank you, Karen. For the next few minutes, we're going to talk heavily about PrimerExplorer version 5 from Eiken. It is widely the most used software to design LAMP primers. It's free on Eiken's website, and there's a link available for you. However, it does come with a lot of limitations. It doesn't design loop primers concurrently. It requires a second serial primer design execution, which I'll show you in a little bit why that's important. It only allows for up to 2,000 base pair sequences, and it doesn't support any UPAX characters other than ATCG. And so previously we spoke about degenerate primers. If you have interest in adding in, let's say, an R or a Y, the software will not allow that. So you have to manually note that location and add that into your design when you go to order your primers. It's also limited to a single execution process, and it only outputs in HTML. So obviously the first step is to go to the link and then go to the version 5 software. And the first step at that point is pretty straightforward. You're just going to browse and find your conserved sequence that you want to design against and select primer design. This parameter sets down at the bottom here I tend to avoid. I haven't found them useful. I would like to speak with anyone that found that useful, and that would be really interesting to find out how you use that. But in general, I tend to avoid that, and I go straight to primer design. Once you have your primer or your sequence uploaded, it will look something like this, and so you can see your full sequence. And in this example, I've uploaded a sequence with 800 base pairs. And within here, if you don't have any mutations to deal with and you're ready to go ahead and design against a completely conserved region, you can go ahead and click Generate, and it'll generate 5 different sets, and then you would click on Display. If you have things you need to work on in terms of mutations, or you want to work on detailed settings, you have to do that prior to generating your primer sets. If you do have mutations you want to acknowledge and deal with, what you can do is go into the software and highlight the mutation locations. And once you highlight and select mutation or conserve up here, it will make dashed lines versus the asterisks of where the mutations are located. If you are looking to design common or specific primers, and instead of just avoiding mutations. So by selecting those mutations on the previous screen, and if you leave it at default, the software will completely avoid any of those mutations. If you require common primers or specific primers, meaning that you would like, common primers basically means that you want to build in and detect both the mutant and wild type. And in order to do this, what the software will do is design primers across at the 5' ends at the F3, B3, F2 and B2, and 3' ends at F1C and B1C, or the internal regions of the primer. If you want specificity between mutation and wild type, let's say you only wanted to detect mutant variant, what you can do is select that in the software, and the software will design primers at the 5' end of the F1C or B1C, the 3' end of the F2 or B2, or the 3' end of the F3 or B3. I would caution when you're doing either a common or specific to heavily empirically test to make sure that you're getting the true specificity that you require. It will not be a black and white in terms of just a light switch that you can turn on and off by designing it this way. You're going to have to probably make multiple sets and test them out to make sure that you have the proper specificity. In order to do this, down here in the right-hand corner are the options to select. So you can leave it at the default. You can select common or specific. And once you do that, you can go ahead and generate and display your primer sets. And when you do this, what you find is that with default settings, right here is where you had the mutations selected, and the software completely avoids those mutations. It does not design any primers on those mutations. Conversely, if you select common designs, it will bury those mutations at the specific locations that we just spoke about, and the specific designs in the same manner. The one thing, if you do select common or specific, it will focus on making primer designs in those locations and not necessarily just avoid mutations. So if you're looking just to avoid mutations and design on a conserved region, I would recommend leaving the default and just acknowledging where those mutations exist. Once you have selected, once you have a set of primers that you want to evaluate, you also, what will look like in a simpler manner here is you'll have your conserved region above and a list of primer sets. And so it'll work left to right, and you'll have, for example, your F3, F2, and then the F1C, and you have a space here where potentially your loop will go. And since Eiken doesn't do it concurrently, you need to select a primer design that has enough space between the F2 and the F1C in order to design that loop primer in a second step. And so you want to make sure you select, if you want loop primers, to select designs that have space. In addition, you want to also select designs that have the largest delta G value for dimerization. So you can find the delta G value for dimerization in this column right here. And I've circled the one with the highest value. And purely in terms of dimerization, that would be a design that I would want to carry on for further evaluation. And you may at this point select multiple designs in order to do so. Or you'll have to kind of balance between having room for a loop design and having the best delta G value. Once you have one that you like, and you select the box on the left-hand corner, you confirm, and you would evaluate those primers for end stability, and the delta G for the end should be no greater than -4. And here I've circled an example of a -3.74. So this whole set I would throw away or set aside in case I can't find and look for something that's better. And you should check the stability of the 3' end of the F2 region, 5' end of the F1C, and the 3' end of the B2, and the 5' end of the B1C. Once you have selected a primer set that you have room for loops, you have a proper delta G for dimerization and a proper delta G for end stability, you'll save that primer set into a text file. And then if you require loop primers, you'll go ahead and reinitiate the PrimerExplorer and browse for that saved file of the 4 primer design. In this case, you will not have primer set options for a loop design. And so you'll go ahead and select primer design. And what will happen is it's similar as before. You'll upload your sequence, but now you lose all of your functionality over on the right, and you can see that it notates where the F3, F2, and the rest of the primers are located on your sequence. And at this point, you can go ahead and generate loop primers and display them. And once they're displayed, you can see that it's a similar screen as before. The difference being that now you have your sequence up here, but you also have the designs from the first 4 primers laid out on top of that sequence. You can see that the loop designs fall in between the F2 and the F1C. You'll also notice that these designs there's not a lot of heterogeneity. You are very limited in your design because of the amount of space that's between the other two primers. And so you'll see that they're off by a few bases here or there. So what you want to do is basically go through the same steps and select the largest delta G for dimerization, and select the boxes on the left-hand side and move on to evaluating for the 3' end stability of those loop primers. So in this case, this top one has the highest, or the lowest value, excuse me, and the highest end stability. And so this would be the loop primer design that we would select. So in this case, again, you save this as a text file, and now you have two files that exist with your 4' design and then your loop design, and you're ready to order your primers. If you run into a situation where you end up with no designs or too many can happen if you go into detailed settings and you start expanding your TM or your length of your primers. You can end up with hundreds or thousands of designs. So when you're in those settings, you just need to change your distances. If you don't get any, you can expand those distances between the F3, V3, F1C, or F2, expand your GC setting. You can change your target range. Worst case scenario, you may have to go back to your target sequence and try and find another conserved region or another area within the genome that may allow you for better primer design. In order to get to the set points, you need to select this detailed settings tab down here. And within this detailed settings, what you'll find is that you can expand the length, the TM, and the GC concentration. In this example, you can see that is labeled as GC rich. So what the software does when you upload your sequence, it analyzes and says it puts it into a bucket, whether it's GC rich, AT rich, or normal, and then it automatically sets defaults based on that. So these are the defaults for a GC rich sequence. These are all, now that you're in the detailed settings, you can expand your TMs and your lengths, and you can also expand this GC percent. So you can see here, this is 40 to 70. Previously, I told you should be shooting for 40 to 60. And so you have a little bit of wiggle room there to move some things around in order to get designs that you're looking for. An alternative to Eiken is software from Premier Biosoft. It is available for purchase. It provides, it's a simpler solution. A lot more things are automated. It doesn't have the limitations of the Eiken software, so you don't have to worry about degenerative primers. You don't have to worry about only limiting to 2,000 base pairs. You can do multi-sequence alignments. It also automatically interprets blast search results. It will calculate free energies for multiplexing. If you would like to try multiplexing, that's a nice tool. And it also allows you to do project management kind of on a local database, so where Eiken is just a web portal. And so if you're ever interested in taking a look at it, it is much easier to use. There's a link here on the slide for you.
Great. Well, that now brings us to our third poll. And moving on to some enzymes. Which enzymes are you using in your LAMP assays? Again, select all that may apply. We have a couple of different BST options, GSP, we have a Lucigen LavaLAMP enzyme, and if you are using something else, we'd be most interested in learning about those, so please go ahead and type that in the chat box. All right, looks like BST right at the top there is very popular, along with the BST2. Great, thank you everybody. We'll go ahead and conclude and close the poll.
All right, thank you, Karen.
Tony?
So now that you have a primer design or primer designs, ideally you have multiple to work from, you need to select an enzyme of choice, and we just spoke about that in the last poll. And some of Lucigen has available are LavaLAMP products, both a DNA master mix and RNA master mix. Those are optimized for an RT reaction or not an RT reaction. We also have OmniAmp LAMP kit, DNA RNA LAMP kit. The master mixes are in 2x formulation, so you only have a couple of optimization parameters. primer design, reaction temperature, and also your primer ratio and primer concentration. These are lyophilizable ready, so you can lyophilize them and take them in the field. The LavaLAMP enzyme runs at a higher temperature compared to BST. It's at 68 to 74 degrees. And once you are happy with what you have, we can work with you to customize for your specific needs. With the component kit, is a lot of the same characteristics. The biggest difference is that we allow more optimization in terms of having the enzyme and the magnesium separated out, so you can customize for your specific targets. LavaLAMP versus BST. So the software that we just talked about were designed and built around BST and its TM. And so BST and GSP both work best around 60-65 degrees, and LavaLAMP works best around 68 to 74. And so those default set points potentially could be better at a different set point for LavaLAMP. And so we've done a lot of work looking at different primers and different enzyme systems, and I'm just showing you a couple of examples here. In the first example, I pulled a published primer set that someone had used and bought the primers and tested them, and what you see is that you can find an assay temperature that will provide solid resolution and fast results in your positives with very little background. Conversely, in the second example, you pull a published primer set and there is zero resolution between positive and negative. This is a fairly common problem switching enzyme systems. And so it is possible, if you want to evaluate a separate enzyme, that a different primer design may be necessary, unfortunately. We went through and we wanted to find out what the optimum TM would be for a LavaLAMP enzyme because it does have a higher assay temperature optimum. So this is an example of an experiment. We ran multiple of these, but in this specific one, we looked at a range, if we focus on the F1C TMs, from 59 to 71. And these are the default settings down here for the Eiken and the Eiken software. And so we bracketed it, and what we wanted to find out is if we adjusted the TM, what would the impact be on the results from using the LavaLAMP enzyme. And so by increasing the TM set point from the primer design, you get faster and more consistent time to result. What you find here, so in this case, I'm just showing group 1, the middle group, which is the default, and the final group. And what you see is as you increase the TM set point during your design, you decrease variability and you can get faster TTRs. Sometimes this doesn't necessarily always look like this. Sometimes your temperature optimum and your assay temperature could be anywhere in this range. For this particular experiment, this looked like this, where you're increasing your TTR as you increase your assay temperature. Depending on the target, that this looks a little bit different, but in general, as you increase your design set points, you decrease your variability and increase your speed. Conversely, with negative reactions, it has a similar impact. Just as your background is just getting slower, you see background go away and become more consistent as you increase your TM set points in your primer design. If you look at the resolution between your positives and negatives, this includes all of the different designs and all of the different TM set points. And you can see that as you increase TM primer design set points, you start to decrease variability and you can get better separation with being able to select, for example, in this case, an assay temperature of 72 degrees and get a resolution of 30 to 40 minutes. So based on all of the different experimentation that we conducted, we found that increasing the TM set points by as much as 6 degrees can improve primer design. Some designs won't allow that much of an increase because your primers are going to get too long, and so you may be only be able to go to 5 degrees or 4 degrees, but you'll still see a marked improvement in primer design consistency and success rate by increasing your TM set points during primer design.
Great, thanks, Tony. So this is our final poll question. If you could choose one technical hurdle that significantly impedes your LAMP assay development, what would it be? And here, could you please select just one? Maybe your primers don't work, too many optimization parameters, poor sensitivity, or you have to purify your DNA to get the assays to work. Maybe you found a great master mix, but it cannot be lyophilized. And if there's something else that you find problematic, go ahead and please type that in the chat box. We'd be really interested in learning more about what hampers some of your assay development. All right, so as we suspected, the primers, which are critical, oftentimes or can not work, and that seems to be one of the top choices there, Tony, along with optimizing the different parameters. All right, great, thank you. We'll stop the poll and continue the presentation.
All right, thank you, Karen. So once you've selected your primers and you have design, you want to optimize your reaction. And the obvious goals for this, for LAMP, is to have a fast time to result for your positives with very little background. And in addition to that, have the best sensitivity and the best LOD that you can obtain. So some of the factors for optimization, we've already talked about primers design, but also the primer concentration and the primer ratio. A common primer ratio is 1 to 4 to 8. Sometimes if you're really limited in your primer design and you have to select a primer that has like a high dimerization or a low stability and can cause some of your problems with hairpins or self-dimerization, adjusting that ratio and maybe decreasing that single primer a little bit can help improve background. A second big knob is reaction temperature and then magnesium concentration. Slightly less important specifically if you're using buffers or enzymes that are purchased from vendors. Reaction pH you don't really have a lot of control over, but you can have additives, betaine or triton, for example. But be careful with additives because some of them, if your goal is to lyophilize, take it in the field, some of those additives are not lyophilizable compatible. So the first step is to take your primer design and run a temperature optimization. At this point, we've been talking kind of on a per design basis. The reality is in practice, what I'll do is design a lot of times 5 designs that I think will work, 3 to 5, because they don't all work. And so you have to screen them. And this is an example of what will happen when you screen. So you see in set 1, pretty much complete failure. And in set 2, you have a high, fairly fast background, but you do get positives and have some resolution. Then finally in set 3, you have a good design that gives fast results under 10 minutes with very little background. This is a pretty common situation, and I've had to go up to 5, 6 designs to find one that really works. So our recommendation is right up front when you're designing is to build multiple designs to screen to find one that will give you a good solid positive with very little background. I also want to mention when you're making those designs, not to do this by hand. Do use one of those softwares. It's really difficult because of the complexity in the 6 primers to try and do that by hand, and that'll create even more problems when you get to this step when you start screening. It may feel like you're going through a lot of steps with the software, but it's a lot better than trying to do it by hand, trust me. Once you have a design that gives you reasonable positive and reasonable negative, design of experiments can help with optimization because of those multiple factors. So setting an objective is pretty straightforward in this case because we're going to try and reduce the positive TTR and increase negative TTR. And then we want to select our variables. So this, if you're starting with a screening design, you're going to select a lot of the variables that kind of come up first, whether it's primer concentration, magnesium concentration, or a temperature, assay temperature. those will have the larger impact potentially, but you need to be able to find your brackets. So running a screening experiment first, and then a subsequent factorial design to determine the interactions, because there will be some interaction with assay temperature and magnesium concentration and enzyme concentration, for example. So it would behoove you to go ahead and use design of experiments if it's possible to help really lock down what is the optimal conditions for your specific assay and primer design. So in summary, LAMP is an isothermal nucleic acid amplification technique appropriate for detection in point of care or low resource setting when rapid detection is necessary. LAMP primer design is more complex and less predictable than PCR, and screening of multiple LAMP primer sets is necessary to identify a successful design. Discriminative target selection and subsequent LAMP primer design guidelines are necessary for the creation of highly sensitive and specific LAMP assays. Adjusting the TM set points during your primer design to match your DNA polymerase's temperature optimum can improve assay performance, and systematic optimization of reaction conditions using design of experiments can expedite LAMP assay development. Some resources that are available, there's many publications at this point on LAMP. There's a previous LAMP webinar that you can find on Lucigen's website, and a multitude of e-slides for the different products that Lucigen provides, all found on the Lucigen website. Thank you for listening today. Any questions, don't hesitate to contact Karen.
Thanks, Tony. At this time, we will entertain any questions you may have in the audience. Go ahead and type them in the chat box. And while you're doing so, we'll address some of the questions that came up during the presentation, Tony. The one that I want to bring forth first is from Chris. Could you clarify about the delta G, negative G? The slides and the verbal presentation seem to be in conflict. And I think he was kind of referring to somewhere around slide 32. I don't know if you want to just jump back quick and take a look at that.
Yeah, so slide 32, at the ends, you want that to be, it should be lesser than -4. I am sorry. You are correct. So you want to have the most stability at your ends. So you want that to be less than 4. So you want to, that -3.74, everything else is correct on that except for that should say lesser, and that is my fault. So that is in conflict. Thank you for catching that.
Thank you, Chris. And then Tony, Cameron brought up a couple of questions about, designing the primers with the Eiken software and having some problems, even if you're ordering 5 to 10 sets and find out none of them actually work. Any recommendations on how to pre-screen these before ordering and testing them in the lab?
Yeah, I found that it's almost always empirical. Unfortunately, I've not run across any telltale signs that can kind of limit that number. It's an unfortunate deal with LAMP that I've ran into. It's kind of a crapshoot. You try to do your best with following as many of the guidelines and rules as you can, particularly with dimerization and hairpins and things of such nature because you have the 6 primers. But in the end, the empirical testing is kind of where we are.
Okay. And then just again about some of the LavaLAMP products, as you mentioned, the enzyme runs at a higher temperature. So maybe it's worth reiteration, how would you proceed, with published primer sets?
Go ahead and order those primer sets and screen them with the optimal temperature. So do a temperature optimization between 68 and 74, similar to the data that was presented. Run that screen, and if there isn't an optimal temperature that provides you with workable positive and negatives, then that design probably is not compatible with the LavaLAMP enzyme. And if you have desire to switch or to truly evaluate it, unfortunately, it probably would mean going back and going through a design process and selecting a different primer set.
Okay. We'll move on then to a question from Julia. How to choose an appropriate restrictase to confirm a specificity of the reaction? Sure. How to choose an appropriate restrictase to confirm a specificity of the reaction. Is there any, like a probe or anything that you can use to identify a specific product? Or
that's going to become
maybe a
difficult
restriction
with
enzyme or
the different concatenators that come out. I've never tried it, to be honest, because of that. I'd have to think a little bit more about that to see if there's an appropriate way to do that.
All right, and Julia, we can, if you want to contact tech support, we'll have your email and we can further that discussion with you as well. And then Whitney had a question. How do you screen primers to check for background
That depends on
reactions?
the instrumentation and technology that you're trying to work with. So the ideal way would be to use a real-time PCR instrument, and then you can run the reactions and determine when background comes up versus your positives. The other modes are mostly endpoint, and so you're going to have to take cross-sections in time, and then you can run gels to determine at each time to see if you have real product versus background. And real product will have a very distinct pattern, so you can run a positive control and compare your banding pattern from your concatenation products versus the background. And the background will either have a smear or have a different banding pattern compared to the positive control.
Okay. Oh, and Cameron mentioned something here regarding one of the last questions, and thank you, Cameron. In the past, they have noticed they've used restriction digest, clone the digest products into a vector, and then sequence them by Sanger sequencing to check for specificity in the region between the FIP and BIP regions. So that's, thank you for, awesome. Thanks for that, Cameron. Any more questions? Go ahead, type them in the box. We'll be happy to address them. And maybe just one more question that sometimes we get in tech support, Tony. You know, how many replicates are really necessary to get representative results when you're analyzing those
what
primer
I tend
sets?
to do is run the first screen, if it's a lot of different primer sets that I'm evaluating, just in duplicate, but then I'll go and repeat that on anything that shows promise with a larger N, somewhere around like N of 6 per condition, ideally. It really depends on how comfortable you are with the data that's coming out.
Okay, and then we have a question from John. Are there any things you can do to reduce the non-specific background times rather than screening more sets in cases where you are sequence confined?
That's a good question. One thing that we've done, you can
evaluate help a lot with that?
Your temperature, but you're already optimizing your temperature. So the one thing you can do is try and lower your magnesium concentration. Sometimes that will have an adverse effect on your positives. Another thing you can do is systematically go through and determine which primer empirically determine which primer is creating the background. A lot of times what I've found is that there's a single primer that's causing the problem. Let's say a lot of times it's one of the FIP or the BIP because they're longer and there's just more opportunity for dimerization and hairpins. To find out which primer that is, and then instead of running that at full concentration, try and decrease that concentration of the problematic primer a little bit and see if you can't decrease that background without sacrificing any speed in your positive samples.
Okay, any other questions at this time? And if not, we'll go ahead and conclude the webinar. Thank you very much for your participation in the polls and in the question and answer session. If you have any additional questions, please email our technical support team at the email address on your screen. And both the recorded webinar and the slides will be available on our website in a few days. So thank you, everyone. The webinar is now concluded. Have a good day.